Thanks so much for coming out to this fill-in talk. They had a last-minute cancellation, so yesterday they said, any chance you could put another talk up for today? So I grabbed one of my favorites that I'm constantly tuning on. Actually, no, this is all Jennifer's fault. She asked for this talk, so I switched to it and had to refresh it. My name is Richard Campbell. I make a bunch of podcasts. Any .NET Rocks listeners out there? Oh yeah, a few hands. So you know, we made this series called The Geek Outs. We still make them. I just don't make as many of them as I used to. I really only do a couple a year now. But back in from about 2012 to 2017 or 18 or so, I would do one a month. Whatever geeky subject the audience wanted. We had voting lists, and I got to work through a lot of different subjects. I'm always reading papers anyway. And this talk, and the fact that I even do talks about this, these were supposed to just be podcasts, came from the moon-based talk, the one at the top. So the moon-based talk was based on a paper from the European Space Agency. Back in 2016, they were talking about that they felt the technology had advanced to the point where we could actually reasonably build a base on the moon that would be periodically inhabited. They compared it very much to Antarctica, that a group of 6 or so could go onto the space, and they'd spend about a month, maybe 40 days, a day-night-day cycle on the moon, because it's 14 Earth days light, 14 Earth days darkness, 14 Earth days light cycle on the moon. So I made that podcast, and that was fun. I make lots of them, it's not a big deal. But this particular one, I got a call from NASA, which is weird. Now, to be clear, I didn't believe it was a call from NASA. I thought I was pretty sure I was being pranked. But then you look at the email closely, and it's like, it's nasa.gov. It really is nasa.gov. So I responded back to him, this guy named Chuck from NASA. And Chuck said that the NASA guys really liked my moon-based talk. And I'm like, well, that's nice. And podcasts have been passed around. It's like, now he only knows me as a podcaster, right? So he says, would you ever consider doing it as a talk? I'm like, yeah, Chuck, I guess I could do that as a talk if you want. Okay, well, do you know PowerPoint? Because we really like PowerPoint at NASA. I'm like, yeah, Chuck, I know PowerPoint. He goes, well, if you'd be interested, we'd really like to have you come and do a talk. And I'm like, okay, well, to who? Like, I'm thinking this is some kind of educational outreach or something. He's like, well, to us. NASA? Yeah. It's your stuff, right? Yeah. So you want me to present to you your stuff. Yeah. All right. So a few months later, I got to go to NASA Ames, which is outside of San Francisco, and in the big board on the way into NASA Ames, there I was, and my mother is proud. It was very cool to, actually be on this research facility. I got to take a tour of it. They got a bunch of they do a lot of aero testing there, so there's lots of different kinds of high-speed wind tunnels and things like that. I met a guy named Ron Andrews who's actually flown stuff to the moon and led a few missions, and a brilliant man. It's a long story and a very enjoyable experience. So the Geek Outs have been a heck of a thing for me, but from this came other conferences saying, I didn't know you did talks on space. And I'm like, I didn't, but apparently I do now. And so they've been going on since then. And it's very enjoyable for me. They constantly need to be refreshed. I literally was changing slides an hour ago because we're in a bit of a renaissance right now. Like, it's a pretty exciting time in space. And normally, if you listen to the Geek Outs, I'm very grounded, like only real engineering, real science. I struggle with this too much science fiction in a lot of space-related stuff, and I'm trying to resist the science fiction, focus on the fact. But this talk's a bit more speculative. So I'm pushing a little further out, saying if we really wanted to be a spacefaring race, that is to say, live and work in space. Right now, we do expeditions to space. Right? They literally call the time on the space station an expedition. You bring all your supplies with you, maybe a few more supplies get dropped off, but it's all short duration. How do we really function an extended period of space where you're not... The fact that, for the most part, astronauts live on a mission clock, that their reality is based on the number of seconds that they have been in space, doesn't speak to being spacefaring. That shouldn't be relevant if we actually get there. Now, we do have to tackle core arguments here, like, why would you bother? Why space is not a friendly place, which is very true. And there are principal ideas on why this is useful for civilization, starting with the most obvious one, which is defense. The Dinosaurs went extinct, this is a Carl Sagan quote, because they did not have a space program. And we do. In fact, NASA actually operates a group called Planetary Defense. It's a real group. That folks I've met a few of them, that this is what their job is, to consider all of the possibilities related to defending the planet. Now, not just from asteroids, although that's a big one, but there are a bunch of other issues out there. They actually did a paper that I turned into another geek out about supervolcanoes, where they said, if the Yellowstone supervolcano ever erupted, like, this is how much damage it would do to the Earth, and we could mitigate that by using geothermal power to keep the caldera cool enough that it would never erupt. Which is crazy, but not impossible, and it might actually make a huge difference. Speaking of asteroid defense, it's not just science fiction. We've actually begun real missions related to that. If you followed the DART mission, this was an actual effort to modify the orbit of an asteroid to see if we can do it, to begin the path of understanding what it would take to actually control that. And so this was done with a couple of satellites. This is actually a video sequence of the last 5 minutes of DART. So this is a binary asteroid system. The large asteroid is called Didymos, and it's about 780 meters across. And then there's a smaller asteroid called Dimorphos that was about 160 meters across, and they are going to impact into it at about 6.6 kilometers per second. And cleverly, they're sending continuous telemetry back. These are photos every minute or so. We're getting frame by frame now, and then one of the frames doesn't finish. The goal here, the orbit of Didymos was about 12 hours around the larger asteroid, and the goal was to change it by about a minute, and they changed it by half an hour. And they're not sure why. It worked too well. Now, part of this is we're coming to understand that asteroids, these classes of asteroids especially, are rubble piles, and so the interaction of all of the rocks amplified the impact and changed it more. It also created a spray of boulders coming out from behind the impact site, some 10,000 kilometers long. They also sent a couple of, that's the impact moment, they had a couple of CubeSats following behind it that they'd released so that they could have footage of themselves doing that flyby. So there's now another mission that left last year called Hera that's going back to this asteroid pair to do further study to understand more about what we've done here. So we're on a path to being able to protect our planet from potential impactors. Of course, there's much more that we want to do with asteroids. At some point, we'd like to get some value from them. There's a limited number of resources down here on the planet. In fact, I've read a paper from a NASA scientist who said that the window to become a spacefaring civilization may be relatively narrow, only the next 50 or so years, because there are certain resources that are essential to spaceflight that are of limited availability. And over time, we'll be using them up until it becomes too costly to do so. And if we don't sort of get over that hurdle where we now have access to the resources of the larger solar system, we may never be able to do it. And so there is some urgency. Taking advantage of the resources that are available to us is important. I would also say that you do need a place to put explorers, because if you don't give them things to do, they get up to stuff. Our society is at its best when there are people, certain kinds of people. Astronauts are not normal humans. I've met a few. They're very odd. Imagine being smart enough to get a degree in engineering and a master's science degree and a medical doctor degree, and then endanger your life continuously, like, for no money. These are not normal people. I'd say, I'm sorry, you've spent all this time and all this money to get all of this education so that you can poop in a bag while floating around. Okay. But when those people are doing those things, not only are they happy, but those images are good for us, that seeing that we're doing more, that we're learning more, that we're expanding the horizons of our civilization, that we are progressing, not just dealing with the day-to-day. It's good for society, and it does create things. Okay, so let's start dealing with the problems of becoming a spacefaring civilization, and I'll use Heinlein's famous quote here of, once you get to Earth orbit, you're halfway to anywhere. And right now, it's still too expensive to get into space. It's hard. It's only a couple of 100 kilometers up. But you've got to be moving really quickly to stay up there. It's very easy to go straight up. The problem is you come straight back down. And you'll notice that when rockets take off, they lean over pretty quickly because most of the energy of that rocket is used to accelerate it up about another 25,000 kilometers per hour to actually be able to fall towards the planet and miss. Now, in science fiction, we talked a lot about space elevators. This would be the sort of ideal case. I've done a whole geek out on these if you want to listen to it. These are basically hovering tethers that happen to touch the ground. The idea that once you had one of these, you would just be sending an elevator up. Now, this is not a normal elevator. This would be about 36,000 kilometers long, made of a material that's impossibly strong. Plus, it's so long, like, you're not pushing button penthouse, and there you go. Right? At 36,000 kilometers long, even if your elevator is moving at 400 kilometers an hour, that's 4 days. And more importantly, you pretty much have to put this right on the equator because rotational dynamics is going to require that. And so, yeah, we could deal with the weather part of that, but that's only the first couple hundred kilometers of a 36,000 kilometer long tether. The far more significant issue is the Van Allen belts. We have a pair of radiation fields around the planet that are created from the plasma coming off of the sun. And one of them is very negatively charged and one of them is very positively charged. And they're very radioactive. They're very powerful belts of energy. When the Apollo astronauts had to go to the moon, they took a very circumspect orbit around to avoid most of the Van Allen belts, and they were moving very quickly so that they transited them in a few minutes. You'd be sailing through those things for more than a day in the thickest part of it. That would be bad. So we need to come up with a kind of radiation shielding we really don't know how to make. And we're also going to create electrical coupling between the two belts when we stick a rod right through them. So this is going to stay science fiction for some time, at least on this planet. There are other places where elevators make more sense. And it may be unnecessary now because we're getting clever with our rockets. Our friend Elon, and believe me, I'm very sad about Elon. I remember the guy who flew his sports car into space. I like that guy. I don't know who this guy is. But this new rocket he's working on is pretty profound. This is Starship, and it is incredibly large. That is 9 meters in diameter. It is massive, and the goal is to be 100% reusable. It does not work yet. They've flown it 7 times, and the profile is pretty straightforward, that the booster lifts the entire vehicle off, runs for about 2.5 minutes, and then it separates, turns around, flies back to the base where it took off from, and is caught out of the air, which is insane. And then the Starship part can go up into orbit, which is substantially faster, do its mission, and then be able to deorbit, handle the reentry burn, and also land on its tail. Now, this would be completely impossible, except that, we've seen them do it. That thing weighs 275 metric tons. It's 70 meters tall, and you caught it out of the air twice so far. So I guess we have to believe, right? Not that everything always goes right. This was the other half of that rocket. Now, this was the second version of Starship. This is the first time it flew. We don't call it V2 for obvious reasons. You would not want to make any Nazi references. But because it was an extended version, about 300 metric tons heavier when fueled, obviously something did not go well. And this was video from the Turks and Caicos of the ship broken up and going back. I'm sure they'll solve it. They keep making progress. It's a very unusual rocket, and if it works, it's dramatic important. And I'd be remiss not to mention the other tech billionaire, our friend Jeff Bezos, his New Glenn from Blue Origin. After 20 years of development, they finally flew it once. And they were supposed to land the lower stage, a la Falcon 9 style, but that did not work out. But the upper stage did make it to space and stay and deliver its mission successfully. Now, that's not quite as large. It's more of a competitor to Falcon 9 than it is to Starship, but it's much bigger than Falcon 9. Falcon 9 is a 3.7 meter in diameter rocket. That's a weird number, but it's specifically the largest number for a cylinder that you can transport on highways. Elon got a really good tax break from the California government to build his rockets in California, but he mostly has to fly them in Florida. And so to not have to ship them through the Panama Canal to get there, he built it at a size that he could send by truck to Florida. And that limits the capability of the Falcon 9. As extraordinary as the Falcon 9 is, it was more than half of all launches and all payload lifted into space last year. And last year, we flew more rockets into space than ever in history. New Glenn is a 7-meter rocket. That's one of the largest payload fairings ever flown anywhere at any time. And if it's as reusable as Falcon 9 and can get down to comparable prices, that opens the door to a lot more payloads, which is interesting. These are the only numbers in this whole deck. This is sort of a rough breakdown of pricing. Back in the 1990s, you were paying about $25,000 US a kilo to low Earth orbit. The old school rockets like Atlas V reduced their prices when Falcon 9 came on the market and got down to about $8,000. There are only a couple of Atlas Vs left and they're spoken for. There won't be any more. Falcon 9 is our mainstay here. Even that $3,500 seems to be high now. Now they're up to 25 reuses of each booster. That's more like $1,800 a kilo. That's why you're seeing so many more missions and actual tourist missions like Jared Isaacman and so forth going up. Falcon Heavy has a better deal, but you're never going to actually lift 54 metric tons with a Falcon Heavy because the payload fairing's too small and they can't make it bigger. That's the limitation of the Falcon 9. That's where New Glenn has possibility. Vulcan is the replacement for the Atlas V. It's built by United Launch Alliance. It's flown exactly twice, and that number is completely speculative. It's what their CEO has told us it's going to be. I think he's lying. And New Glenn's number is also completely speculative. We don't really know. What's not speculative is the price of the Space Launch System. That's a number given by the General Accounting Office. It is the most expensive way to lift anything into space, so needless to say, that's the one that Congress is advocating for. NASA has tried to ditch this rocket system for a couple of decades, but they don't control their own budget. The US Congress does. The Space Launch System is built from parts of the old shuttle, and NASA, to stop their programs from being canceled, got really good at parceling out their projects into every state in the United States, which means that you now have several hundred congressmen that are motivated to keep their people employed to not let you cancel anything. So when shuttle ended, and it had to, it was too dangerous and they couldn't make any more of them. They weren't worried about killing the astronauts. They got lots of astronauts. They only had 3 shuttles left after they blew up 2 of them. And so that they had to end it there, but they didn't want to lose the jobs. And so not only were they required to make a rocket, but they were required to make a rocket out of shuttle parts to keep all those things in place. That's why SLS exists. Perhaps this new administration might finally break that, but that would take some political savvy, and I haven't seen a whole bunch of that. The Starship Super Heavy, which I just showed you the clips of, what would the price per kilo be? This again is speculative, we don't really know. If it's a fully reusable rocket, so all that you're doing is a bit of maintenance and refueling, you're talking in the tens of dollars per kilo. That means a flight to orbit for a person at the first class ticket range. Like, that's a pretty big deal. And it opens the door to more things. Starship's so big that it has its potential cargo area, and we don't really know how big it is because it's still in the experimental phase, but based on the rough shapes being 9 meters in diameter, that's as much volume as all of the International Space Station on one flight. It took 60 flights to build this thing. It's the biggest thing we've ever put into space. It's insanely complicated. It has lots of problems, and it's going to end. So it's the size of a football pitch. It's about 450 metric tons. It's about 900 cubic meters of pressurized space inside of it, and they lose things in there all of the time. They spend a lot of time looking for stuff on the International Space Station because it's just too big. Like, they've learned, don't make them this big and use a better inventory system. And mixing Russian, American, and European parts is really not that good of an idea, actually. So this has been our primary laboratory in space now since 2000. We've had humans in orbit that entire time, mostly because if you left this station on its own, it would rapidly break down and be unrecoverable. It has to be continuously manned, or we will lose it. However, some of those parts are now well past their lifespan of 20 years, and they're starting to break, mostly Russian components. And so the original plan was to run it till 2024. You will notice it's already 2025. Then they extended it to 2028, and now they're talking 2030. The Russians are disagreeing, but the Russians are not very agreeable right now. And in 2030, they're going to have to deorbit it. There's been some conversation about trying to keep some of the parts up, but it's very likely they cannot dismantle it. This station was designed to be put together in orbit. It was not designed to be taken apart in orbit. And one of the things that happens when you go into space and you put two metal parts right beside each other, tightly enough that they're completely sealed, is that they actually chemically interact, and they are now one piece of metal. And you will not get them apart, not without a lot of violence. So very likely in 2030, this entire station will be deorbited intentionally. SpaceX has won the contract for the deorbit vehicle. It is a modified version of the Cargo Dragon, much enlarged with way more fuel to be able to decelerate the station enough to target what they call Point Nemo, which is a point in the South Pacific furthest away from any land masses, and it's generally where we deposit our larger space debris. That's where Mir went down. That's where Skylab was supposed to go down, except they never got there in time, and it scattered across Australia instead. Now, to be clear, this is not the only station. There is another one. The Chinese have the Tiangong space station, which they built because they weren't allowed to play on ISS. It's very much a copy of the Mir station that the Russians used to have. There are 6 people on it right now. The NASA has an initiative called the Commercial Low Earth Orbit Destinations Program, which is really saying, we don't want to build another space station, but we will buy time on whoever can build one. So they have a bunch of guidelines. They're actually providing budget for people to do the research, and a number of groups have proposed stations. Jeff Bezos' group's station is called Orbital Reef. It is dependent on New Glenn, which up until last year I would have said is a huge pacing item because New Glenn doesn't work, except now it's flown once. So that's actually a 7-meter diameter station. This is 3 of them connected together. It would not normally be this big. 7 meters sounds like a good idea, but one of the things we've learned about being in free fall is you really need a handhold in reach. If you have an empty 7-meter wide space and you stick yourself in the middle of it in free fall, you cannot get out. Doesn't work. Right? So you actually have to build out the interior so that there's always space in reach. The 3-meter diameter ISS parts, which are really based on the limit of the shuttle, mean that there's always a surface you can grab onto. Keeps you safe. The Axios Space is a group of ex-space station folks who are trying to build a new station by actually assembling against the existing station. This seemed like a really good plan until they ran out of money. Now they've got one component almost finished. They're trying to get enough funding to get it going, but they're going to shuffle some things around so if they miss the space station, they'd be all right. But their original plan was to build a few components, because berthing means you don't have to have propulsion on every unit, right? That you can actually bring it up, connect it to the station using the arms, get it all assembled, and then when they're finished, they'd have one propulsion unit, and they'd make a separate free-flying space station. It's a cool idea. And I bring up one more, and that is just recently, and that is the vast Haven 1 space station. So a guy named Jed McCaleb, another billionaire, only this time it's a crypto billionaire. He's the guy behind the Mt. Gox exchange. Has decided that he wants a space station. Must be fun to be a billionaire. So he founded VAST in 2021 and set about buying a bunch of smaller space companies that already had skilled people and equipment, and they're bending metal to build this station. And they're scaling it to fly on a Falcon 9 and to be crewed by a Falcon 9 as a tended space station without any NASA support of any kind. I mean, they're bending metal. I don't know if it's metal you could live in, but that's where we are with stations. Okay, let's talk a little bit about the moon. This is my favorite picture of the moon. You'll notice this is the far side of the moon. That's not the dark side of the moon. No side of the moon is dark. It's just the far side of the moon. But because I'm resistant to science fiction, I always ask questions when I see pictures like this, starting with, who took this picture? Because that's a funny spot. How do you do that? This is actually a photograph from Discover, which is the Deep Space Climate Observatory satellite. It's in the L1 Lagrange point between the Earth and the Sun. It's a solar observation satellite, but somebody was smart enough to put a telescope on the back of it, because when you're in the Earth-Sun L1, you're 1.5 million kilometers away from the Earth, but you're in a gravitational balance point so that you're always facing the Sun and always have the Earth directly behind you, which means when you look back at the Earth, you always have a full disk view. So they did put it's a telescope because it's 1.5 million kilometers away. It's a long way away, and it routinely takes photos of the Earth and sends them back, so you get these cool disks. And every so often, the moon whizzes through the frame. And so this is one of those photos. And if you get up close to this, you'll notice that on the right side of the moon is a bit of a green haze, and that's because they don't have color cameras on these satellites. It's actually a black and white camera with different filters, and it's 4 photos that it takes to build an RGB picture. And in the time it takes to take those 4 photos, the moon moves. And the green photo is taken last, and that's why there's a bit of a green haze, a little distorted out of it, which is really tricky CGI. Like, who would do that? Of course, we've been to the moon before, you may remember. You probably don't remember, you're too young. Even I'm too young. The Apollo missions ran from 1967 to 1972, and 12 men, white American men, walked on the moon. 11 of them were test pilots. One of them, this one in the corner here, Jack Schmitt, that guy is a geologist. He's the only scientist to ever set foot on the moon. He was supposed to be on Apollo 18, but they canceled Apollo 18, and so they bumped him up to Apollo 17. When you ask a test pilot what you're thinking while you're on the moon, they are mostly thinking, please God, don't let me screw up, because that's how test pilots think. But when you put a scientist on the moon, what are you thinking? Well, I'm a geologist. What I'm thinking is, I really want to look at the rocks. And that's what Jack did. This is Jack. You'll notice Jack is dirty, because Jack looked at the rocks so hard he fell on them a lot. Over and over and over again. Over 3 days, Jack looked at rocks. He didn't like the visor on his helmet because it's coated in gold and changed the color of things. So he kept opening the visor. Now that visor's there for a good reason. It's because the sun, we have no atmosphere on the moon, and if you look at the sun, you will not look at anything ever again. And so you leave the visor down. And because test pilots, please God, don't let me screw up, they never lift their visor. Jack's a scientist, and the only photograph we ever have of a man's face on the moon is Jack. Because Jack really wanted to look at the rocks. Actually, go back to this picture. You see the side of the helmet here with all this stuff there? So Jack wanted to lift his visor, but he didn't want to burn out his retinas because you can't look at rocks that way. On your left arm on the Apollo suit, there's these cards, and it's literally minute by minute what you're supposed to be doing while you're on the moon. And as he finished each card, he started ripping them off and sticking them in his helmet to block the sun so he could look at the visor, to look at the rocks. And he found the best rocks because he's a geologist. He had 22 hours, over 3 days on the moon. He found more important rocks than anybody else because he tried to teach test pilots how to look for rocks. But you don't find things that are important to science by going, Eureka, I found it. You look at stuff and go, what the hell is that? And you need to know a lot about rocks to know that's wrong and it's odd. You need scientists to do that. And Jack did a great job of that. There's the whole the entire time that he's on the moon. You can actually listen to these on YouTube. There's all the conversation. And, you know, those astronauts are really cool and calm, right? And so you always hear Capcom say, hey, Jack, when you get a minute, would you put your visor down? That's all they say. Not, you dumbass, but that's basically it. Why'd they cancel this? I mean, it was amazing, right? And the real reason was that it was a military mission to prove that the American technology is better than the Russian technology and Soviet technology. And every time they flew it, there was a very good chance people were going to die, and that would ruin the plan. This lunar excursion module was insanely dangerous. There was a mitt full of failure modes in this thing that were not recoverable. There was only 3 days worth of oxygen and food on board, and the fastest you could get a rescue mission up to them was more than 3 days. So they were dead if anything went wrong. Nixon seriously considered canceling it after Apollo 8, when they just flew around the moon, because now they'd beaten the Soviets. Then they talked about canceling it after Apollo 11, when they landed on the moon. And finally, they did cancel it after 17, this mission. But we're going back to the moon. The Americans are calling it Artemis, which is the sister to Apollo. Clever. And these are a series of missions using that crazy rocket I mentioned, the Space Launch System. This mission, Artemis 1, has actually flown. It's the only time this SLS has flown. It was unmanned, but it did send the Orion capsule to the moon. They did some pretty cool science with this. Our computers are dramatically better compared to the 1960s and 70s when we were flying trips to the moon, and so we know more about manipulating gravity and different tricks to move through gravity wells. So the Orion did some maneuvers we'd never done before and proved the gravitational models correct, that they could do some very clever, high energy efficient ways to fly things around the moon. The second mission is Artemis 2. This is going to be a replay of Apollo 8. You'll notice it just goes around the moon and back. It's a free return trajectory mission, exactly like Apollo 8. And 4 people are going to be on board that craft. They have already been selected. 3 Americans, one of them a woman, and 1 Canadian. Lucky. This was supposed to fly in November of 2024, and now they're talking September 2025. The rocket has been assembled, but there are issues with the heat shield, which is something that the astronauts are highly interested in. So they're still solving some problems to perhaps get this flight to go at a price of something in the neighborhood of $4 billion a flight. The third mission, Artemis 3, would be the landing on the moon again. The shape of this mission has already changed dramatically. This was also supposed to fly in 2024, then it was 2025, now they're saying 2026, it's probably 2027. The pacing item is the lander. They're not trying to do what Apollo did and have everything on one rocket. They want to have a lander separate from the manned vehicle that comes to the moon and back again. And so the current winner of the lander is SpaceX, and this is a modified version of Starship to serve as a lunar lander, and it is 50 meters tall. Those are people down there. This is all fuel tank. There are engines here for landing. This is the pressurized volume for the payload, and the people watch that first step. It's a doozy. So there'll be an elevator on the side of it, supposedly. This is a ways away from actually working, and the only way to get a vehicle that big there is you're actually going to have to lift it off from the surface of the Earth and then refuel it in orbit, then fly it to the moon, leave it in orbit around the moon, and then the Space Launch System takes the astronauts up, flies the Orion capsule to the moon, meets the lander, they go down to the surface of the moon, do some stuff, come back up, go back on the Orion capsule, and go back, which seems inefficient, but re-entry capsules need to be small and strong. There's no way that lander could actually come back to the Earth reasonably. The issue here is that gravity is your enemy now. When you leave the moon, you're moving quite slowly, about 2 kilometers a second. In space, that's slow. That's just enough thrust to actually have you start moving away from the moon until you get grabbed by the Earth's gravity, and then it keeps accelerating you and accelerating you and accelerating you. By the time you get back to the Earth, you're moving at about 30 kilometers a second, and it's very hard to stop. You don't have enough fuel. And so we use these big heat shields, and you skim through the outer parts of the atmosphere to slow down enough to actually be able to come back to the surface of the Earth. We have no solution now to actually go back into orbit around the Earth after having been at the moon. All we have is heat deflectors enough to be able to just go straight back in again. But we also need to refuel, and nobody's ever refueled. There's something about these pictures that reminds me of a code of conduct violation. I don't know why, but yes. So SpaceX wants to make tankers, so they use a bunch of the fuel to get up there, but they have enough left over to pump it into the ship you want to use. Again, it's never been done before. There are a bunch of complexities to it. Let me show you. This is a video of the inside of a Falcon 9 liquid oxygen tank during ascent. So it's under acceleration right now. See if you can tell when the acceleration stops. This is the problem. The fuel doesn't stay at the bottom of the tank where the pipes are. You can't pump what isn't at the pipes. So whenever we do this on rockets and you stop them, you stop running the engine for a while and you start to drift, the fuel floats around. Before they can relight the engine, they'll fire little jets like Veneers, and they'll just accelerate the vehicle a bit to let the fuel all settle before they'll try and light the rocket engine again. And if we were going to refuel, you have to do the same thing. You have to settle the fuel before you can actually pump it. There's been a couple of different design ideas. Here's another code of conduct violation. This one sort of makes sense because all the plumbing is at the bottom there, so if we just sort of meet up the bottoms, maybe we can pump that way, but then how do you accelerate the vehicle? And the other thing is you're in orbit. So every time you accelerate the vehicle to sell little tanks, you're changing the orbit. Make sure you accelerate the right way, because if you accelerate the wrong way, then you're not in orbit. There are proposals to actually build proper refueling stations, which kind of solve the problem. The other way to settle the fuel is to rotate. So what if we built a small structure that the tanks can couple to, and then you turn it to settle the fuel, and now you can pump it. This also gives us a bit of infrastructure in space. This is a fuel depot. Now you can do the commercial thing and say, I'm paying X many dollars per ton of liquid hydrogen or liquid helium or liquid oxygen or liquid methane. I don't care where you get it from, but if you get it here, this is what I'll pay. Maybe you lift it from the Earth, maybe you can extract it from an asteroid, but I can create a market here. I could have a refueling depot, more than one, around the Earth. I could even have a couple around the moon. But as you start having that infrastructure, you create a market space, and it opens the possibilities to other ways to solve problems and to actually generate revenue from it. So rotating structures for refueling are probably a good answer. There's some challenges there. Again, none of this has been done. We will probably see the first significant fuel transfer using Starship in the next 2 years. So this is imminent, right? These are problems they need to solve right now for the missions they've committed to with NASA for the Artemis missions in order to make this thing work. What are we going to do on the moon this time around? Well, we're not just doing the flags and footprints thing. We're trying to stay for longer. We're trying to do more science. They've made pictures of some of the cool things to do. This is actually based on a lander that Blue Origin proposed, which is a 3-part lander, so that they had to leave as many bits behind as possible. The actual real interesting thing in this picture is the fact that that astronaut is kneeling, because the Apollo astronauts could not kneel. The pressure inside the suit didn't let them bend their legs that far. That's why when you see them on the moon, they're kind of doing this thing, the Michelin Man effect. It's because the pressure of the suit itself restricts your ability to move. So one of the proposals here is they believe they have suit designs now robust enough that they can fully articulate knees, that kneeling is even possible. The other problem is that they want the suit to last. After 3 days on the moon, Jack Schmidt's suit was essentially a ruin. The regolith of the moon is so abrasive, it got into all of the hinges, all of the clasps, and ground them apart. The suit wouldn't last much longer. The longest proven lifespan of a suit was 22 hours. NASA wants the new suits to be 800 hours. People really don't know how to do that. We're still trying to figure that one out. One of the best ideas right now is to keep the dust off the suit, or rather to push the dust off the suit with electrostatics. This thing is highly electrostatic, and there's been some demonstrations now with a sort of a fine mesh on the material, and you hit a button, and literally the dust jumps off of it, which is cool. But again, all technology we need to improve if we're actually going to stay up there. The current mission idea, if we're actually going to build a base on the moon, is to build it on the South Pole, specifically the Shackleton crater. This was the Blue Origin proposal, so some construction sites, some landing zones, because they're leaving behind the bottom of the lander each time they do this, so you're going to need some parking spots because you're going to fill them up. Or how about this? Don't build a lander to leave stuff behind, which is what SpaceX actually proposed with that crazy rocket. It doesn't leave stuff behind. The Shackleton crater is directly on the South Pole. This is a time lapse of a year of the Shackleton crater. You'll notice that the edges of the crater are lit almost continuously, and the inside of the crater never gets light. And the argument is the inside of that crater is filled with water ice. Now, you should ask the appropriate question. Who took this picture? This is a composite picture made by the Lunar Reconnaissance Orbiter. Every time it passed over Shackleton, it took the shot at exactly the same time. So it sits really still. But it showed that the rims of this crater almost the entire year round have light on them, so it's a good place to put solar panels, and the inside of the crater never gets light. This crater is bigger than you think. It is 21 kilometers across. You can put a bunch of Londons in this crater. It is big. And they figure there's several billion tons of water ice in there. And water is the current most interesting asset. If we can actually extract water from the moon, we can make oxygen for breathing, so we don't have to carry all of it with us. And the water for drinking, because it's a kilo per liter of water. Thanks, metric system. And that's a lot of mass to haul up. If you collect the water there, you don't have to carry that stuff around. And of course, you can split it into hydrogen and oxygen if you want to make it into jet fuel, into rocket fuel. Like, there's choices there. So being able to access water in some place other than the Earth opens the door to a lot more missions. All right, other projects, when we talk about infrastructure, we need a GPS system for the moon. ESA has proposed one they call Moonlight. Is that what they called it? Yeah, Moonlight. So this is a combination of GPS and cellular communications. It's only about 16 satellites, and they're in exotic orbits. The moon's gravity is wobbly enough that you can't put stuff in low orbit. It'll not stay. So you have these unusual orbits moving back and forth, but the point is, because the moon is so dramatically smaller, it's only about the same amount of surface area as the United States. You can have 3, with 16 of them, you'll have 3 in view at any given time, which means you know exactly where you are, both on the surface of the moon and in immediate area around it, and you should be able to communicate with it reasonably reliably, which means you carry less equipment. You'll carry 1 backup system of navigation and communication instead of 2. So you save that weight, you can do a bit more work. And then we start building bases on the moon. Elon wants to build Burning Man on the moon. Actually, it kind of reminds me of Space 1999. You remember that show? Are you old enough? Have you watched it again? Don't. Your memories of that show are dramatically better than that show. You ruin your childhood memories of an early science fiction show if you watch it today. It's terrible. It's like Kentucky Fried Chicken. Your memories of that chicken is way better than the actual chicken. Anyway, this is not the kind of base we're built. ESA's proposal was a little more feasible. This is an inflatable habitat with a fixed airlock that they would then bury in regolith because the radiation levels on the moon are significant. It's fine if you're only going to spend a couple of days there because you're only ever going to get to do that once, and that's enough. That's your lifetime radiation dosage right there. But if you're going to spend a month, we need to protect you, and so the ESA design was we soft land this thing, then we use robots to bury it in a meter of regolith. That's sufficient radiation protection. Another approach would be to use the moon itself. This is the Marius skylight. So there was volcanic activity on the moon in the past, and this volcanic activity is what made the Mars, the big dark areas on the moon, are actually lava flows. And when those lava flows subsided, the lava flowed back down into the magma wells that it came from and left behind lava tubes. This happens on the Earth as well, and it happened on the moon. The Marius skylight is a point where the lava tube was close enough to the surface that some kind of impact broke it open. So that's 65 meters across and 80 meters deep. And they figure the tube's about 50 to 60 meters wide and goes on for kilometers. So rather than having to put down a habitat and bury it, why not put it down there, slide it into the tube? You have all the radiation shielding you want and a lot of space. And you don't have to deal with micrometeoroid protection, that the moon will do that for you. So it's not as sexy as these cool Burning Man bases on the surface, but living underground is likely what we'll have to do anywhere we go other than here until we come up with better radiation solutions. What to do on the moon? I mean, we already had Jack up there, and clearly we could have more geologists. But the bigger thing to do on the moon is to figure out how to extract more resources than just water ice. So we're talking about construction, using robotics to be able to make surface of the moon. Making landing pads will be important because spraying debris around when you land causes problems. The gravitational well of the moon is so low, 2 kilometers a second, is entirely possible if you blast hard enough to toss a rock that will go all the way around the moon and back to you at velocity. So don't do that. Making landing pads will be an important part of it. But our goal is to get more resources off the moon, because we've already done a bunch of spectroscopic analysis to show that there's lots of silicon and iron and calcium and titanium and manganese and phosphorus and aluminum. In fact, all of the materials to make pretty useful products. So can we prospect? Can we mine? Can we refine? Can we manufacture? And there are some benefits to being at lower gravity for certain kinds of manufacturing. In fact, that array of materials that are readily available on the surface of the moon are pretty much the stuff that goes into solar panels. And modern solar panels are primarily single crystals, and those crystals would grow phenomenally in reduced gravity. And the more perfect the crystal is, the better the solar panel works. So we could build really high-grade solar panels off the moon functioning in 1/3 of gravity. And if you use it with those materials, now you could have as many solar panels as you want on the moon. In fact, the Japanese proposed, let's put a band of solar panels all the way around the moon, because that's crazy. But a more practical thing would be to build as many as you need for the power you need at the time. But it'd also be interesting to build them for the Earth, not on the surface of the Earth, though. If we built the factories there and built these solar panels, then we could use a linear accelerator to send them back to the Earth. This is not huge science. We only need 2 kilometers per second to actually leave the moon and head back to the Earth, which we can do pretty easily, as long as there's not a human involved. That's about 100 Gs of acceleration. You make people into strawberry jam when you do that. But solar panels don't mind, so we can accelerate the solar panels that way. And you can see just faintly what we do with them up at the top of the Earth there. That is a space-based power station. This is called SPS Alpha. This is about a gigawatt of solar power being collected and then transmitted by microwave down to the surface of the Earth. This is one of the things Jeff Bezos has been very keen on. He wants to move heavy industry off the Earth, and one of those heavy industries is power production. Because this array, and it's huge, this is about 5 kilometers across, so it's impractical to build lifting from the Earth because it's too heavy. But if you're lifting from the moon, where the gravity is so much lower, this becomes a lot more feasible to do. You're going to need to do some robotic assembly. I'm not saying any of this stuff is easy, but now you can make a gigawatt of power 24 hours a day from geostationary orbit. It's never nighttime. So this is zero emission energy. Now, you're going to beam it down to the Earth with microwaves. It's going to land on an area roughly 10 kilometers across. Now, this is not intense enough to like fry birds in flight or anything, but you're probably not going to want to walk around in there. We'll put up a fence. But it's a gigawatt of power, 24 hours a day, no emissions. Also, it's somewhat steerable. So, say you have a natural disaster site and the current power system is down, you can set up one of these rectenna arrays in a day and start sending power into an area that needs it, rather than shipping in diesel generators and all those other things. But also, once you build that kind of thing, you don't just have to send that power down to the Earth. You can use it in space as well. All spacecraft have to be able to move around, they have to have 3 things. Then you have to have a power source of some kind, a propellant of some kind, and an engine of some kind. Now, often when we're doing chemical rockets, we're combining the power source and the propellant into one. If you take liquid oxygen and liquid methane and combine them, you get a velocity of fuel running out the back of the rocket in a big hurry, and that's your propellant, and it's also your energy. But if you look at electrical propulsion, Hall effect thrusters and so forth, you're using solar panels to gather enough electricity to plasmify some xenon and accelerate it out the back of an engine. And those solar panels are heavy, and they take up a lot of area, and you need a lot of energy for that. Well, what if the energy source wasn't on the vehicle? What if the energy source was the array? And you just beam the energy to the spacecraft. So the spacecraft gets to be lighter, and so you get sort of solar sail effect, where I'm putting the energy onto the vehicle. Now, it's only going to work up to a certain distance, but that distance would be completely feasible between the Earth and the Moon. So I could start building out the infrastructure to be moving stuff back and forth between the Earth and the Moon. We talked about the return from the Moon problem. One of the ways you could make this work is to have a stationary power plant, well, basically an orbiting power plant that's providing the energy to be able to decelerate. So this is more speculative, but we have all the ingredients. We already transmit power with microwaves routinely. We've tested all of this. It's completely feasible, but start to think about the broader view of what you could use all those pieces for. So once you've got the Moon more or less figured out, and you're starting to look for more resources, if you can do all those things on the Moon, you can probably do them on asteroids. This is a speculative drawing of grabbing an asteroid to extract resources from it. There are lots of different kinds of asteroids, and so it depends on the material, and there's a geek out on this if you care. It's unbelievably huge quantities of material, stuff that's very rare on the Earth, very common on many different kinds of asteroids. Most common kind of asteroid is called a C-type. This is an asteroid we call Mathilde, and we have gone to the surface of this asteroid. It's mostly organics, nitrogen, potassium, phosphorus, and water. So useful asteroid, not that hard to get to this and then try and extract resources from it. Our friends Didymos and Dimorphos were S-type. These are rubble piles, they're rocks, and they're full of silicates and other useful mining resources there. And then there are the M-types, the metallics, Psyche being the largest of it. We believe this may have been the remains of a planetary core. It's in the asteroid belt. In 2023, we sent a mission to it to explore it, mostly nickel iron, but also platinum-class metals. Now, it's one thing to get there, and it takes a few years to do that, and then what? It's not likely we're going to try and move these things closer to us. That's hard. These things are heavy. It makes more sense to actually extract the resources from it and just send the resources. So there are folks that have been building devices to extract in freefall or in zero-G. So this is the Honeybee by Transastra. Parts of this have actually been built. So they're using optical mining. So collect solar light, focus it, and vaporize the rock, and you use gaseous extraction to separate the different compounds, combine them with halides to make specific compound fluids, store those fluids in a bag, and ship them separately. And they'll naturally freeze up as the temperature drops after they've been burned up. So these are relatively small asteroids, but it's a good way to start, and you can pull resources from them. Now, once you have those resources, what do you do with them? Well, one option is to send them back to the surface of the Earth. It's not the best option. It's a fairly bad option because it's pretty expensive to do that stuff in space, and then you stick it back down a gravity well. That's a nuisance. More likely is then we start to mature orbital manufacturing. Because we put a lot of constraints on the stuff we put into space by assembling it on the Earth and then folding it up origami style inside of those payload fairings to bring it up. As soon as you can actually build in space, you don't have to follow those rules, right? There is no air. We don't have to be aerodynamic. Our devices will look very funny. They'll probably be mostly spheres, and they'll be lattice works, especially if we can just build, we'll initially only be able to build structural elements. The electronics and things we'll probably still bring up from the Earth, but they're light in comparison, right? So the smart, expensive bits will be brought up. The larger construction bits can be built up in space until we get better at building stuff in space. And if you get to the orbital construction part, now we can start to actually build out the infrastructure to utilize the whole solar system. The logical place to do this is actually the far side of the moon. This is where a space elevator would work well, fairly easily, out of very reasonable materials. You know, we talk about carbon nanotubes and things for building a space elevator on the Earth, which we've made like several millimeters of and shown that it's sufficiently strong. All we need now is 100,000 of them, 37,000 kilometers long. You could make a space elevator on the moon with Kevlar. That's strong enough. It's just the gravity level is so much lower. Why put it on the far side of the moon? Because once you're up on the counterweight of the elevator, you're basically positioned to essentially fling yourself anywhere in the solar system you want to go. It's just a timing thing. Depending on which way you're pointing and where you want to go, you get about half of the velocity you need to get to Mars or to get up to the asteroid belt. So you build this infrastructure. You've got mining facilities on the moon to get some of your resources. This is probably a good construction site, and you start building out those extraction machines and sending them around the solar system, and if necessary, bringing resources back here. If you want to do it the easy way, you just let it impact the moon. Because for the most part, those resources won't be destroyed. They'll just be scattered a bit. But, you know, you already knew how to mine off the moon, so now that you've put a new mineral bed on the moon by throwing it there, you can scrape it up and use it. And so we also learn more about humans. One of the things we learned from the International Space Station is that humans don't do well in free fall. We typically only let them stay up there for 6 months. In those 6 months, that every day they exercise 2.5 hours. That's why you know astronauts are weird, because they're willing to exercise 2.5 hours a day. I'm not willing. And still, their bodies degenerate. One of the biggest problems you have being in orbit is cerebral spinal fluid. You have a pair of glands inside of your brain that produce a fluid that washes your brain, takes the debris away, and it carries it down into your spine where it does exchange with your kidneys and you pee out the debris. And this doesn't work in free fall. It also doesn't work for bedridden patients. Like nurses learned a long time ago, if you've got someone who's bedridden, you need to sit them up every day. And one of the things that happens when you sit them up each day is it causes that cerebral spinal fluid to rotate and help to keep them healthy. So when you're on the space station, that cerebral spinal fluid builds up in your head. It's why all of those astronauts look so puffy. Also, it presses against the backs of their eyes and it bends their eyes. So they all go up to the space station with perfect eyesight for the most part, and they carry several different levels of glasses because over the course of 6 months, their eyes change shape, and they have to switch to different glasses to be able to see. Astronauts are weird. And then after 6 months, you come back down, and you cannot walk because you haven't stepped on your feet in 6 months, so they really hurt. And your vestibular system is messed up because you've been floating for 6 months. And your fluid's now moving around again, so your face changes shape and your eyes change shape, and it takes a year to recover, sometimes longer. Now imagine sending astronauts to Mars. I'm not saying they wouldn't go, they're insane. It takes 6 months to get to Mars in free fall, and when you get there, there's nobody to help you. It's not going to go well. So we need artificial gravity. Now, this isn't science fiction. There's only one way to make artificial gravity, and that's to create a rotating structure. The question is, how much gravity do we need to make? Because we don't really know. We only know free fall and 1G. We don't really know anything else. And if you need to make a rotating structure that works at 1G, You need the rotation to be relatively slow, or you have some Coriolis effects that are really hard on people. And so typically, when we talk about a rotating structure in space that would create a G, it's 100 meters across. That's really big. And we've never built anything that large, and it needs to rotate at about 4 RPM. But if we could go to lower gravity, if people were still healthy with that, all this gets a lot easier. One of the things we could learn having humans on the moon is how well the human body functions at 1/3 of a G, because that's what you've got on the moon. 1/6 of a G, sorry. It's 1/3 on Mars. It's 1/6 on the moon. So some gravity. But we need extended testing. So putting people on the moon is a way to do that, to keep them in 1/6 of a G and go, okay, this is the problems that we have. It's different from free fall. Maybe we can make a simpler vehicle. We've explored ideas on how to build rotating structures on space. This is a proposal called Nautilus, and it's basically based on space station parts plus this rotating inflated donut that would provide enough gravity for people to be comfortable on. So you have free fall areas and you have gravitational areas. And those gravitational areas where you'd sleep, so your body is a little healthier and you're more prepared for dealing with gravity wells when you get wherever you're going. The Martian did a pretty good example of this with their Hermes. Again, this is science fiction. Mark Watney should be dead. And can we stop rescuing Matt Damon? I don't know why we keep doing this, but the Hermes was actually well thought through. And that rotating structure is further back there, and they didn't fill in the whole circle. They actually had 4 modules on it that were rotating. One of the things they don't talk a lot about in this idea is that everybody, with the exception of a few genetic mutants, and there's a couple of astronauts that have this mutation, is space sick for the first couple of days. Your transition from being in gravity to being in free fall makes you ill. It's one of the reasons you're seeing that most of the tourists, the billionaires that get to go up to the space station, only go once, because billionaires don't like being nauseated all the time. And if you were going to build a ship like this where you sleep in a gravity well but you work in free fall, does that just mean you're sick all of the time? Or would you get used to that? Because nobody's done this, right? We don't know what would happen. It's one of the things to experiment with the new space stations. Can we build a centrifuge space station? There was a proposal to do this on the ISS, but then somebody finally clued in that if you have a rotating structure on a microgravity lab, you mess up the microgravity lab. So they never built the centrifuge. So we need a smaller, dedicated space station with a rotating structure to do all of these experiments. We have a lot more to learn. But if you solve this problem, and you know how to build in space, you don't have to live everything from the ground up, and you know how to extract resources from asteroids, you've built all these pieces. We're talking decades of work here, right? That we've built up our space yard on the moon, that we're collecting resources. We can start building bigger things. Like, going to Mars is kind of dumb. Why? You went all this way to go back into another gravity well? Like, I'm all for the science of it. But living there? Why? If you want another place to live, you're better off building it. And you just did all the things to know how to do it. You just need to scale it up. So Gerard O'Neill, back in the 70s, proposed this idea they call the O'Neill cylinder. And it uses all the ingredients of what I've just walked you through. It's just big. This would be 32 kilometers long and 8 kilometers in diameter. It rotated about 2 RPM. But it's room for 5 million people living in like a suburban condition. If you want to live urban, you could get 20 or 30 million onto it. You want to go into space, you take an elevator to the central axis and off you go. It has reflectors to collect solar, to provide natural light onto the surface. There's clear parts on this rotating structure. It's counter-rotating. There's 2 cylinders rotating there so that it doesn't destabilize. And it's a habitat. We have the materials in the solar system to build 100 million of these. Why would you go to a planet? Make your own. Make a bunch. You want to put a lot of humans out there? You want trillions of humans? You put them in 10 million units. I would suggest the orbit between Venus and Earth, because there's more light there, and there's very little debris. And you can have a lot of them. Now, living is going to be a little weird, right? The curves are all wrong. The weather is going to be interesting and selectable. You're going to have some choices of which you can operate that way. And you can pick styles of living. Like, there could be more urban environments and less urban environments. Production of food is going to be a challenge. Closed loop Systems have never worked for us yet. We're kind of messing up the one that came with, but every time we try to build our own, we haven't succeeded. But you have all the ingredients. This is not that speculative. It's the logical sequence of events for each of the pieces. And I wanted to stay away from science fiction. I wanted to sort of paint a picture of the steps that we're taking right now and the choices we can make in the next few years can get us here. I hope this was useful for you. Thanks so much for coming out.